Welcome to qnawire.
Hi, so over here we want to calculate what is going to be the Gibbs free energy for the following reaction, which we're going to have iodine as a solid plus 2 of silver as a solid. That is going to produce 2 iodine ions in aqueous solution plus 2 of silver plus in aqueous solution. So in order to get this result, there are going to be several ways to do it. In this case, since there's no context given, I'm going to use the approach of finding the result for Hess law. So the standard free energy for this reaction would be equal to the standard free energy of formation of the products, in this case, 2 times the value for iodine in aqueous solution, plus 2 times the delta G of formation of silver plus in aqueous solution, minus the energy of formation of the reagents, which are iodine as a solid, minus 2 times the delta G standard of formation of silver as a solid. So in this case, the values that I'm going to be employing for the energies of formation are going to be on Chang and Overby 13th edition chemistry book. And actually, the only values that we're going to take are these two in red. Why is that? Because iodine as a solid is a substance in its standard state, so its standard free energy of formation is going to be equal to 0. Same thing goes for silver as a solid on its standard state. So the delta G for the reaction is going to be equal to 2 times the free energy of formation of the iodine ion, which turns out to be minus 55.9 kilojoules per mole, plus 2 times the energy of formation of silver plus. A small correction over here, I misread the table. It should be minus 51.67. Yes, minus 51.67 kilojoules per mole. And for silver plus, the standard Gibbs free energy of formation is going to be equal to 77.1 kilojoules per mole, which is going to give us a free energy of reaction of 50.86 kilojoules. Alternatively, you can calculate the delta G for this reaction as employing the standard redox potentials. In this case, it will be minus n times Faraday's constant, the standard potential for the cell, or the standard potential for this reaction. In this case, for example, the redox potential associated to the reaction of silver plus 1 electron producing in aqueous medium, producing silver as a solid, is going to have a redox potential equal to 0.80 volts. In the case for iodine as a solid, plus 2 electrons to produce 2 of iodine in aqueous medium, is going to have a value of 0.54 volts. So the E0 for the reaction that we have in hand is going to be minus the first reaction, since we're going to have the inverse of that, plus the second reaction, and the number of exchange electrons would be equal to 2. So in this case, it would be 0.54 minus 0.8, which gives us minus 0.26 volts. Remember that these values of the standard redox potentials are going to depend on the tables that we're employing, and the result may differ a little bit from the actual value of the calculation. So over here, what we're going to get is minus 2 electrons, which are going to be exchanged, Faraday's constant, which is going to be approximately equal to 96,485 joules per volt mole mole of electrons, in this case we have 2 moles of electrons, of course, times the standard potential, 0.26 volts, which would give us a delta G naught of 50.172 kilojoules. As you can see, both of the results are going to be quite close, and their difference is going to be given essentially by the reference values that we're employing. So with that, it would be all. Just use the answer that is more correct to the context that you're employing. For example, if you're looking into thermodynamics, Hess law, and stuff like that, use approach 1. And if you're employing right now, or you're seeing in class, redox reactions, Nernst equation, and so on and so forth, use the second approach. So with that, it would be all. Thank you very much and have a good one.